Great, thank you, John. So just a little bit about what I'm going to talk about today is TileDB Cloud, but how I came about it, where we used it. Started with our platforms project funded by the ARDC, and some of the technical and implementation challenges that we had with this project, how we came about resolving those, and a bit about lessons, but also give a demonstration of the TileDB Cloud as well. So the project background itself was to provide multi-resolution capability to users. So seabed itself is a collaborative initiative that brings together data from participating partners. And one of the partners that we're working on with this project is the GMRT, the Global Multi-Resolution Topography. It's a service run by Lamont Doherty Earth Observatory. And we were looking at a way to enable users to have a customized gridding solution, so they can pick their spatial area, choose their gridding methodology, choose their projection, and choose their resolution. For this project itself, metadata was really key. It started out as being really key for enabling users to, with a choice for dataset level filtering and point level filtering. For example, remove points that have say an error of higher or less than X. But really, to make this project work, we needed an efficient data storage mechanism. Why did we really look at this project in the first place? So grids are static, and we've definitely found all the time that users want a different resolution than what is provided. A scenario, sorry, that was provided to me by GMRT was that users themselves really, they're finding a lot of people still just download the raw, grid it to how they want it, to their desired resolution and projection, but they then might also modify the underlying data and then distribute that modified data to someone else who will then do their own gridding and potentially any additional modifications as well. So this starts to question the provenance of the data and what is the original source, because there's now starting to be lots of duplication. So it started to lead us to think a bit more about how can we try and sanitize this data provenance and data management nightmare. So along with those challenges, we had a lot of technical challenges. So our team, seabed, is in the midst of migrating to the cloud, and we're still really figuring things out, like anyone does. So it's a new thing, a new toy, a new system. The foundation data itself is a mixed bag of open and proprietary formats, and the open formats that are there aren't well supported. Some are 30 years old, and existing APIs don't work with object stores either. Metadata, yeah, we didn't have the time in this project to resolve this issue. Even though it was quite critical, it was not as critical as the actual data, the foundation data itself. So we had to do the bare minimum to enable discoverability. And in the end, we used STAC, the Spatiotemporal Asset Catalog, which is becoming more of a thing for geospatial data. So what we did was just smush together what little metadata we did have into that specification. But we still didn't get to resolve the issues with all the differing vertical data. So that's for future work for us. But the biggest technical challenge here was compute. As I mentioned, we're migrating to the cloud, but we don't really have any systems for us. So, but with this compute for this project, by some standards, we didn't have a lot of data, probably only 3 to 4 terabytes. We just took a sample set, but still a short time frame. But for this talk, I'll focus more on the compute and the storage architecture that we did for this project. So our solution, we came across TileDB, and there's two components to here. TileDB Embedded and TileDB Cloud. So we had a variety of different disciplines of users who use different APIs, and they all exhibited a desire to still point directly to the data and do their own customizations, like their own personal filtering and their personal gridding. TileDB Embedded as a storage architecture solution is it's under the hood, it's an n-dimensional array store. It's similar to ZAR, but has a lot more features inbuilt with it, such as data versioning. There's more APIs, so you can think of pick your language almost. So I mentioned a bunch here: C, C++, Go, Python, R, Java. For this project, I focused on the Python bindings. But also has a lot of other integrations like GDAL and PDAL, Dask, as well as Spark. Now, TileDB Cloud itself really helped us simplify things as far as security, ensuring that our data on AWS isn't going to be abused. But it makes it easier for us to handle the sharing permissions, the compute, and the software. TileDB Cloud also, it provides a bunch of different utilities, not all of which we used in this project, but it has lots of tools for monitoring data access, which is quite useful for entities like GeoScience Australia that really need to show that data is being used to get continual funding from the government. I think my experience today is demonstrations of use is the amount of downloads, and coming into this day and age, downloads can mean a very different thing. But the interfaces that TileDB Cloud also provide is an interface into versions of your data, different versions of your data, such as arrays, Jupyter notebooks, machine learning models. Governments love record keeping, and GA internally uses TRIM, the Total Records Information Management, as a tool. And one can also think of TileDB Cloud as a solution that can be used here as well, in that any of your document records management can be stored within the cloud and managed as an n-dimensional array. So a document can just be a zero-dimensional array object or a one-dimensional array object, and then versioned through time using timestamps. So this is some of the offerings that they have. So next slide. So what did it do for me? It took care of the complexities, largely being deployment. I probably needed to have looked at a persistent state machine, and if we needed to scale out the compute, I'd need to have a look at Docker. This leads to more testing on deployment, and how do we handle errors? We probably need to add in something that we can spin up and tear down machines on demand, add more machines to a cluster if required, then tear them down again when finished. Then we have to think about pricing, the logging. Where does it go? What do we need to do? So we'd also probably need to have servers to help manage a cluster, and then another server to help manage the computational task workflow. So we then need to start investigating tools such as Dask, Luigi, Airflow, Celery, Flight. There's a bunch more. But I could ignore all that and just focus on some of the core problems that the project had, and one of which we came across, even some unforeseen data problems. We discovered duplicates. No one thought that this could occur, and there's no telling how much in our archives or anyone else's archives are affected by that problem. And existing APIs to that data just treat it as additional data, so that it's quite difficult to discover. And these duplicates actually feed the GMRT process, and this can lead to incorrect statistics regarding densities of measured values, as well as bias in data aggregation. We also had inconsistent schemas from the data that was provided to us, which came down to different levels of processing. Some had been processed to a further degree than others. We had different as well as data provided was internal to a survey, was processed with different versions of licensed software, which is annoying if licensed software can't keep backwards compatibility. It starts to throw in the question, like, we really want trustworthy data, but at that point, it starts to irk me a little bit as there's inconsistencies in the methods of processing itself. Then we have permissions. We need to share it with sample users. S3 permissions, it's not the same as a Linux file system. It's very different to just using chmod, which is much easier. What I've had used in the past, it's typically a JSON config file. You just need to know knowledge of the S3 API calls on how to make your data secure, public, shareable, etc. So the items I've mentioned above, I pretty much could ignore. So this picture here isn't comprehensive. It is an exhaustive breakdown, but it starts to paint the picture of where the project itself could dedicate the time. So I mentioned we've got these old legacy formats. APIs weren't really usable in a cloud context, so we had to write our own. We wrote a bespoke metadata decoupler, a bespoke metadata, data decoupler to convert. We needed to produce a searchable data catalog as well as a front end, which was the whole point of this project, to provide an interface for users to do gridding. Oops, previous. So TileDB Cloud, focusing here, like what did it really do for us? Well, it handled, for me personally, a lot of the compute and deployment. I didn't have to think about it. It came with a Jupyter Notebook service. You don't need to use it. It is when you need. It did provide a way of interacting with the data, especially data that I'd not really used before. But the Jupyter Notebook services that TileDB Cloud provided catered for different use cases: geospatial, genomics, and medical basic data science. And this Jupyter interface also acts as the client from which we can define computational tasks that we can get executed either locally or remotely. So with that, you can still use your own device, and there's an open source API in Python and R that you can use to log in and then define tasks that you want to be executed. Now, for executing remote tasks, and this is where the smartness of TileDB Cloud comes in, the magic, is that we can define functions. They call it a user-defined function, and you register it with TileDB Cloud. Any remote jobs that you want to be computed can pick up that function, automatically deploy and execute it. So I don't have to think about Docker. I don't have to bother with it at all. But a really neat feature of these functions, workflows, is that they can be shared with other users who can then reuse it without even them having to worry about building, deployment, maintaining. So for AusSeabed, this is a huge potential in that participating partners can run the same user-defined functions without needing to build and deploy or hiring specific skill sets. So they too can concentrate on the core business. I think that's a key message here, is what is it you're trying to achieve, and focus on that, and then everything else is noise. But if you're trying to build everything, it becomes quite difficult when you have limited resources. So as an example, here's a screenshot of one of our workflows. The light blue are tasks that are finished, green is what's currently running, and gray is waiting. Now, all of these dots are machines that have just been spun up automatically within the cloud, pulls my user-defined function and executing a process and then returning. So it looks complex, but I'll say I didn't really do much except for define a list of tasks to do using a for loop. So it can be as simple as that, so that anyone can really have that scalable computational capability. So in this example, there's a few hundred data files that we need to process, and we're actually summarizing the acquisition dates of all the data files. So I need what is the start and end date over all the data files for this singular survey. Each array itself might contain hundreds of thousands of soundings, each with its own timestamp. So we're finding the min and max for each array, and then again for all the arrays, and it's a kind of a MapReduce framework here. This task graph also depicts the dependencies. So TileDB Cloud is orchestrating the execution and manages the task dependency. So those dots in gray are not going to execute until its dependency has been met. So I think at this point, for me, when I was doing this, it became quite a oh wow moment, how simple it was to get the kind of scalability that I used to have in working on NCI's supercomputer, but without the mess of having to set something up. And I didn't have to manage a server, didn't have to manage the internal orchestration like I normally would have had to do if I was using MPI. So I'll give a little bit of a demonstration. Oops, got it. So this is the Jupyter Notebook interface that TileDB Cloud offer. I'm just using a small server at the moment. It's only about 8 gig of memory and 2 CPUs. But typically what I would have to do is, okay, we've been given a survey, what files do we have? And just find the files. In this instance, we've got 27 files located in these 3 stores, but they're pretty dumb files. They're just raw binary files that actually the format specification was developed back in the early 90s.
Josh, can I just interrupt for a second? Would you be able to zoom in a little bit into the Jupyter?
Sure. Does that work?
Yeah, that's a bit better. Thank you.
Cool. So you don't need to worry too much about the code. It's more the process of what I'm achieving, what I'm doing in a simplistic way. But the first task is like, I need to be able to try and read these files in parallel. I need to get some basic metadata about the file. So it's pretty much producing an index into this file. So the first thing we're going to execute is some tasks. So I just need to produce some metadata about the file, and that's what all these dots are doing. That's the visualization, and I'm just asking it to compute. And green, it's now running. And these machines that are just, I think I'm running this, yeah, no, these are machines running externally. So they're spun up in the cloud for me, one's done, and in a few more moments, the others will be done. But it has meant I'm not using the resources on this machine. This is merely acting as a server and then pushing the execution elsewhere. There we go. So you can see all I had to do was here's an objects, do a loop, and then tell it do this. Pretty simple. So in order to output the arrays itself, we're going to be doing it in parallel. So TileDB allows the workflows or allows data to be written to arrays in parallel. It's really smart. But I'm going to define the array specifications up front. And these are the attributes that are going to be a part of these point clouds. And in this instance, TileDB have 2 different types of arrays, sparse and dense. This dense array, think of like a 2-dimensional grid where the axes are going to be ping and beam identifiers, like 0 and 1. It's very similar to a normal array access if you're slicing an array, for those that have done that before. Again, this one's going to be done locally. It's pretty quick. There's not going to be much effort to do. So this will execute on the client here itself. And there we go. It's done. So I don't need to spin up machines for some of these simpler tasks. But we're also going to do the same for sparse arrays. So here, we're defining a sparse array to be accessed using latitude, longitude coordinates when you want to pull information out. So it's great for those that are aware of geospatial terminology, but also some of the integrations. So PDAL I mentioned before is a tool that can read these sparse arrays if they're using coordinates, geospatial coordinates. So much the same, execute. So there we go, done. Now this part of the workflow would be then telling it for all these end files, I need you to convert it to a TileDB array. And this is, for this survey, this is kind of what it looks like. Bit complex. We're doing it in parallel. I'm limiting it down to saying only have like 80 things run at once, but partitioning it out to say I want one node to read maybe 1,000 pings and another node to read a different 1,000 pings. I'm not going to execute that one because it will take a bit. So we're just going to have a look at just 2 of the files. So we're going to do essentially the same task workflow, and this is what it looks like in a simpler fashion. And now to execute. So again, I got stuff being spun up in the cloud automatically for me. They're executing the user-defined function, which is unpacking this binary format and restructuring it and then pushing it out to a TileDB array. That's these ones up here. These ones down here is we're then doing a density, like a cell frequency. So we're looking at what is the density of the soundings that we have within this data format. So I think one of the pieces that GMRT do is like for every pixel is say how many points are located within a particular pixel. So what I'm trying to give the impression here is that these data files are not optimal. Hence the reason why convert to TileDB. But it also brings these files into something. So here we go. Here's the first 2 done. These are all, the next task is running, and I might kill this soon. Actually, I don't need it to finish. Taking too long. There we go. Moving on. Oh yeah, so logging. Don't need to worry about it either. It is provided to me. So here in killing a task off, it spits out an error back that we can go and assess. If there was a bug in the system, it's not like it's completely silent. So I've opened the array, this dense array, but what I'm going to do here again is interactively show like what I'm a time comparison between the old and the new. So hopefully this doesn't take too long. I should have preloaded that, but just watch the amount of time, and then I'll execute this cell, which should be much quicker, like in the order of 10 to 20 times quicker. And this is where our major requirement for the project is to be providing this customized gridding solution directly from point on the fly. So I'm going a bit more into the storage itself here as our reasoning. As you can see, it is slow trying to read from these original file formats. Python is also not the best to be trying to read such raw binary on this, where it's records that are scattered throughout the file. Well, there we go. So it's come through. All right, now let's watch this one. There we go. 10, 20 times quicker to get all of the data for this file. So it demonstrates the power that we can get in utilizing modern file format architecture that is native to working in the cloud. So if we want to slice this array itself, this will read it. This will actually go and read the data again, but I'm going to ask for pings 50 to 100 and all beams. I don't know much about, I'm not a marine scientist, so I don't know a lot about the makeup of the actual sensor itself. But I think of a ping having an array of beams, like almost like a charge coupled device on a camera. It's just a full array that measures something. But as you can see, we can now easily slice this thing. But now we'll have a look at it from another geospatial context. So we're going to create a sparse array. Oops. Array does not exist. Oh, yeah, I did not create. That's okay. I can ignore that one. Come back. Here we go. Sorry, I've lost the. Here we go. That one. There we go. I was hoping to do it quicker, but I forgot to create it. So now we're writing this new data structure into a sparse array itself. Take a few seconds, and now we're going to read it. Oops. And we can see that the bounding information, latitude and longitude, are here in the non-empty domain. And just like before, we can do a slicing. This time we're using longitudinal coordinates and going to get all latitude for that dimension. And here we go. So it, again, very, very quick to read. Now this one is of interest. Now, a discrete global grid system is not a lot of people have been working in this space, but I'm thinking of it, it's more of an index into data itself. So Uber have designed one called H3, Google have designed one called S2, and here I think it was a bunch of New Zealanders who have defined this global grid system. Don't want to go into it too much, but I just want to demonstrate the actual full, this is proof of n-dimensional storage. We're going to create something that has a 16-dimensional axes sparse array. Let's see, hopefully no errors. So here we're unpacking this data frame, creating new coordinate system and writing it to disk. And now we can see what's the non-empty domain of this. Now, these might not make much sense, but if you're interested, you can contact me later. I can point you to a paper. But essentially, if I scroll back up, these codes on the right-hand side here, a spatial index. So this code means it's a resolution 15 and is globally defined, uniquely defined across the entire globe at half-meter resolution. So there's a square that is roughly half meter by half meter, that is this ID. And this is where we can start to measure density on a cellular level. And these coordinates here indicate it's a hierarchical context. So at that level, we're talking continental scale. And there's 6 of these defined over the entire globe. And the further we go to the right, the finer resolution that we get. So it's a hierarchically nested cellular structure. Kind of confusing, but has some real world purposes for data index. And same deal, we can index this data structure using a completely different coordinate system and pull information back. Now back onto our part of the workflow itself. So the spatiotemporal asset catalog requires you to have some statistics associated with the data set itself, more around to give people an indication of what's the internal content, but it can also be used for filtering. So we're actually going to do some statistics. Again, we have a user-defined function. I'll show you that shortly. So we're going to set up a task workflow. I'm going to visualize what it looks like. And now we're going to ask it to compute. So all of this is, again, being executed remotely. The only one that is true at the end is when we're gathering all the information together, where it's a tiny task just to group things. But there we go, pretty quick. But it's machines being spun up automatically for me and then torn down when they're finished and returning the results, which look like that. So we can see that for the X attribute, which is the longitude, that's the minimum, maximum. We have how many points are in this data set, what is the total, the mean, standard deviation, variance, skewness, kurtosis, etc. But it's across every single attribute, which is why the point structure looks like this. It's defined for every single attribute. So if you want to do this locally in the machine, it can take a while. But what we also can do is now attach the results of the statistics as just a JSON document on the metadata itself. So we open up the array and attach the metadata. Pretty simple. But how can we really start sharing this data more easily within TileDB ecosystem is that we can register it. We still pay for the storage. It's got nothing to do with TileDB. It just provides better access control for sharing and reporting, and then cleaner compute calls because I don't have to pass around tokens. So we're going to create this one. Yeah, and then I need to go back up and grab an array name. And they're now registered. So if I come into the interface here are two arrays that have been registered. The dense one is 8 meg. The sparse one is 10 meg. This is down from originally probably 50 meg of data that we received for that particular file. So compression is awesome. But it is comparing, it's not apples and apples. We're comparing a data structure that is completely raw and uncompressed with something that is, but we are storing a lot more data within these arrays. We can have a look at the arrays itself, where its original location is, what's the TileDB array URI. So if you want to use with UDFs or even your local and using TileDB Cloud, you can use the TileDB array itself, the URI, because it provides the token access. Provides information about what the schema is. So we can see the dimensions here are ping and beam. In this instance, we had 908 beams and 908 pings and 400 beams. And most of it is using Z standard as the compression. And then we have 27 attributes. So it's a pretty sizable spreadsheet, if you want to think of it like that. A little bit of metadata. That was the statistics I produced on it. Activity, it's only been little bits and pieces with it. And then sharing. So this is where I can share. This is all programmatically available as well, but I can share with the user, get their username, and then select what permissions they have. So it actually makes this quite simple. So I can still have a secure S3 account, but then share it with another user or organization, which could be any of the members within seabed. So activity. So I mentioned reporting. Now we can see all of the costs here. So to calculate, let's go to reduce. I mean, we're talking less than a cent. Thing ran for 4 to 5 seconds, but everything is documented. So even as far as 7 seconds just to calculate the attribute. And then because I'm doing a recursive functionality statistics, it's there's several bits to the task workflow itself, which we saw, but everything is defined, logged. So we can then start to see who's using the access, who's using arrays, if we want to share it with the community. And it gives us a kind of validation of these arrays are useful, these arrays are being accessed quite a lot, or what data itself is actually being utilized and accessed. But we can see a cost for ourselves as well, anything that's going on. So nothing is hidden. So I'll come back to here. Now, did mention other pieces, so other APIs. So SQL, so don't know if there's many SQL fans online, but you can also use SQL to access the exact same arrays that I'm doing it with Python. So, and I can even, through TileDB Cloud, they offer an SQL service to be run as a delayed function. So I can ask it to, essentially, I want to calculate the sum of the Z attribute. And this is the TileDB array itself. So I mentioned the TileDB URI has a different URI for permission settings. And this will go and execute an SQL statement. Okay. That one. So now we're actually just going to compare the results. Is it the same as what we did in our normal other statistics? Yes. So we can say it's pointing to the same data and we're doing something similar. It's logical. And we're going to execute a different kind of offering that TileDB have as well, is that it can open the array for you, do filtering, subset, and give it back to you. So again, you don't have to have all of this handed client side. It can be done externally to you and return a subset of it. And you don't have to worry about the mess of then opening up the array. And as part of doing that, we're then also going to do a sum. Now this time it's not the same. It's got nothing to do with TileDB. It's actually got something to do with Python. So this time we'll do the same result or the same query and then functional execution, but convert our Z attribute to float 64 so we can get higher precision as far as doing mathematics on this array, which is just a sum. And now it's identical. Now, as far as complex workflows, so here is one. It's just a sample that TileDB actually have on their website. As an example, you can make them as complex as you want. And here's this really funky tree. And now I'll ask it to execute. It's not doing much except for telling a node to sleep for a random amount of time. So hopefully we don't get a lot at the 30 seconds. But you can see everything is running in parallel. Dependencies are retained. Nothing is run until the dependent target has been resolved. And it is just happening automatically for us. So as far as simplicity goes, this is why I see as a major benefit into using a system like this, in that I've not had to spin up anything. I've not had to develop a PC. I've not had to develop the software that we can then spin up machines on demand and tear them down and deploy software. I've just got down to what I want to do, which is convert some data, do some statistics and make it available. But on a grander scale that I did not have to worry about the complexity of the computational structure itself. I just say, here's a list of things to do, go do, and a server is spun up or then executes all this for me, and all tasks are spun up automatically for me. So it's probably the simplest thing I've ever come across. It is really cool. And I think one of the other things I've noticed is, so while I'm using a software as a service, I'm getting billed for this, been running this machine for 2 hours and it's only 24 cents, which is probably good at the moment because the US dollar is not too good against the Aussie dollar. Thank you. But it's been quite cost effective that I've even been using it personally for, like, I do lots of things on the side of interest, data analysis, and it's been quite cost effective for me. But I've also seen this is also a service that they can provide as a license. So if you have your own infrastructure or you want it to go somewhere into your own infrastructure, you can purchase from them to actually have this thing customized and deployed to your entire needs, which is pretty cool. So I'd like to see if, I don't think GA will build their own service, but I think they'd be definitely interested in making this a bit more open to internals of GA itself and making use of this as a computational system. But when you start to think of there's potential within the ARDC and users who could even look at this. So I'm using AWS, but it doesn't need to be. It can be pushed into any kind of system that you'd like. I'll leave it there. Actually, there's probably one bit I wanted to know. So UDFs. So if I look at the preview, so here is a UDF. I've written in Python. It's pulling it down. It's stored in TileDB array, and that's all it is. And you can actually see the code of what I'm actually doing. So it's quite useful to. It's got the same sharing permissions that you can do with someone, activity, what is being used, etc. So it's, as far as an interface, I've not explored machine learning models or further dashboards or sharing workflows. I've really only scratched the surface on it. So, but I'll come back to the slides, and only got a couple left. So what do we get from this project itself? There's a lot more than just what we're looking at from the project. We're now unlocking the full potential of the marine data and providing people with more data than they've ever had before, which was just X, Y, and Z. We've seen for our own purposes, we can reduce the complexity in building scalable workflows without having to build the architecture. Sharing can go beyond just source code on GitHub. We can then share the computational execution functionality within TileDB. So I mentioned before, like, this is quite beneficial and potential for our seabed for the members. A part of it is, hey, we've got this thing, you can execute it too without deploying it for yourself. We also learned a lot more about metadata and really pushed as to why it's important. It's more informative to users, so we can do better filtering, but having actually structured metadata allows simpler queries. We don't need to define one ourselves. We can pick some that are out there in the community itself. We have got more informed QA/QC processes. As I mentioned before, we've discovered abnormalities in the data that no one had seen before, but we only found that out when we started unlocking the data itself. I think there's another big piece here in the data itself. So I've mentioned metadata, consistencies in how we process the data. So we're feeding back to the community as to, here's the demonstrable purposes, reasoning why you should process it in a consistent fashion. We've seen differing vocabularies, finding that error and uncertainty are called the same thing in this field. We also saw that some algorithms were explicitly tied to how the data is acquired, but it doesn't mean it was a showstopper. Not at all. It actually opened up, hey, well, we can do it this way, which is the dense array functionality. So we can feed data in a different way to users that need it that way. And that also led to additional development of sub-level product definitions. So we can describe different data storage dimensionalities, which improves our provenance. So we know what data sets have been created from what and all the way up the food chain, and then who's using it. I think provenance is probably a really critical piece to this community here in knowing everything about a point, where it's come from, how it was produced. Because at the end of the day, some of this data can be used for generating maps, but they really want quality information so people don't run aground, I guess. Now, I'd like to sort of also thank TileDB. They've provided a lot of assistance and answered a lot of my questions. They were in different time zones, but they were very responsive to my queries. They are on Slack. Give them a shout. But a big thank you to the ARDC who funded this project and provided me the opportunity to give this talk. We uncovered a lot more about the data itself and exposed a lot of other technologies that can really be a game changer for our seabed and potentially others as well. And thank you.